So here, okay, what we have now is I'm going to present a more general version of the factor theorem, okay? I'm going to present a slightly more general version of the factor theorem, okay? So that's what I'm going to do now. It's actually very convenient to have this version. The other version was correct. This one's a little more applicable, as you'll see. Oh, wrong button. There we go. Okay. So let's suppose again you have a non-zero constant a, a number. B, that's also a constant. Okay. Then by the division algorithm, okay? By the division algorithm, right? If we were to divide a polynomial, capital F of x, okay? Any polynomial, if you divide it by another polynomial, you get a quotient and remainder. So in particular, by the division algorithm, if we were to divide it by d of x, right? Which is a times x minus b, okay? If we were to divide it by this, right? Then there would be a unique quotient q of x and a unique remainder r of x that fits this equation, right? That's what the division algorithm says. Not only that, r of x, okay, will either be identically 0, it's going to be 0 always for every x, or the degree of r will be less than the degree of your d of x. Now, d of x is degree 1, so r of x would have to be degree 0 in that case. So in other words, r of x is going to be 0 or a non-zero constant. I don't know what that constant is, so let's call it c. Then substituting, what we get is this. Okay, that's what we get here. All right, but can we figure out what that constant c is? Well, yeah, we can actually figure that out. Okay, just like when we considered the remainder theorem from earlier, it's just the same idea. Can we figure out what the c is? Well, what if I replace x with b over a? Okay, if I did f of b over a, right? What I get is a times b over a minus b, right? That's what I'm going to get. Times q of b over a plus c. So I'm taking this equation and replacing x by b over a. Keep in mind, a is not 0, so it makes sense to do this. But what's going to happen, though? Well, you probably saw what was crossed out already, but I erased it. So I'm going to cross it out again. The a's here cancel, right? They cancel, and we're left with b minus b, right? Times q of b over a. We're left with this plus c. But of course, b minus b is 0, right? B minus b we know is 0. So we get 0 times q of b over a. But we get plus c. So we get 0 plus c, which is c. Okay. Now, what is this telling us? This is telling us altogether that f of b over a is equal to 0 plus c. And so c is f of b over a. That's actually what the constant is. Substituting, we get this. Sort of like a general remainder theorem. Okay? Okay, so that's nice. And from there, we can get this slightly generalized factor theorem. This generalized factor theorem says a polynomial, right, is going to have a times x minus b as a factor if and only if this part, f of b over a, is 0. Mostly because this is the remainder. And it's a factor if and only if the remainder is 0 when you divide it. remember the original version, right? The original version of this theorem, the A is essentially 1. I might have called B A, but I wrote it this way. This was the original version. Although I think instead of B here, I had A, but it's really the same idea. So that's what we get here. Okay. Okay. So that's what we get here. All right. Okay. So this is what we get. This factor theorem. Now we're going to use this. If I remember correctly in this example, what we got up to was what the LCD was. Okay, that's what we got up to. Right? We got the LCD to be this. You know, last time that's what we did. Okay. All right. So from here, right, since we know what the LCD is, we want each denominator here to equal the LCD. That's what we want. Each denominator to equal the LCD. Okay. So from here, we're going to get, so from the first rational expression, right, what we're missing is 6 times x minus 1, right? So we're going to get 2x plus 1 times 6x minus 1. Excuse me, we have to multiply the bottom by 6x minus 1, right? That's what we're missing here. Okay? You know, we have 6x plus 1 squared, but we're missing the 6 times x minus 1. Okay? So now we're going to multiply the bottom by 6 times x minus 1. Okay? And remember, whatever you do to the bottom, you have to do to the top. So we're going to multiply the top by 6 times x minus 1. And that's why we get this. Okay? For the second one, right? For the second rational expression, remember, we factored the denominator last time. But you can see we're missing 6x plus another 6x plus 1. We don't have 6x plus 1 squared here. We only have 6x plus 1. So we're missing a 6x plus 1. What do? Multiply it in. And when you multiply this in, you do the same to the top. Okay? That's what you do. All right, so that's what we do here. So now, okay, what we can do next then is we do that, and this is what we end up with. Okay, this is what we end up with. Okay. All right, so from here, that's what we get. Okay. Now from here, right, we want to add these two together, right? Since we're adding these two, we want to add these two together. Okay, now what is this sum going to be? Well, let's see. So when we add, we're combining the numerators, right? The denominators are the same, so we leave it alone. We combine the numerators only, okay? So what do? Well, since we want to simplify the numerators we add, we have to multiply each of these individual products. So we multiply those, so we get 12x squared minus 2x plus 6 times x minus 1, that's over here. X times 6x, that's 6x squared, plus x times 1, that's just x. 2 times 6x is 12x, 2 times 1 is 2, right? That's what we get here, okay? From here then, what we get is, you know, we combine like terms, right? After we multiply. When you combine like terms, we have 12x squared, 6x squared, right? Those are like terms, minus 2x and 6x here, plus x plus 12x, that's from the second product, minus 1 plus 2. And from here, we get this. So when the dust settles, this is what the rational expression is. You know, again, we have to multiply these products here, right? Because we want to know if it's simplified. Okay. Now, looking at this, we could try factoring the numerator. You know, you could probably try the AC method. Do I recommend you do that? Well, maybe recommend is not the right word. Here's a better way of saying it. We don't have to do that. right? We don't have to do that because we have our factor theorem. Namely, from here, we can actually determine if 6x plus 1 is a factor of the numerator and if 6x minus 1 is a factor. We just have this factor theorem, right? Basically, our f of x here is the numerator. So for 6 times x minus 1, let me write it in. What do we have? We have a times x, right, minus b, okay? With f of x as our numerator, we're going to have 6 times x minus 1 is a factor of the numerator, capital F of x, if and only if capital F of b over a is 0. Well, by comparing, you can see that b would have to be 1 and a would have to be 6. B is 1, a is 6. B is 1, a is 6. Okay, that's what we get here. Okay, so we plug it in. We have 1 over 6. So is f of 1 over 6 equal to 0? Well, by direct calculation, it's not. It's not. And because it's not, that tells us 6x minus 1 is not a factor of the numerator.